we are ready to do the merge sort. Yeah. So now you understand the, why we need to do this kind of operations. Yeah. Yeah, and another way people can do parallel computing. Yeah. All right. Here we do not go very far on that direction. Yeah. How to merge two sorted arrays, yeah, given two arrays that are already sorted. How to get a new sorted array that contains all the elements. Yeah. Here, we need to use the order information. Yeah. That kind of information is very valuable. Yeah. The structured data, very valuable. Yeah. The question, how to use that ordered information. Yeah. Yeah. So here we want to connect it to our old, yeah, we have learned three sorts. Yeah. So let's make connection to one of the three sorts. Yeah. Which one can be used to help us understand the current problem? Now, we need to choose the appropriate, old experience to help us understand the current problem. Yeah. So here, do not use any sort that does not make use of the order information. Yeah? So when you choose the right one, we want to draw those sorts that do not use any order information. Yeah. Three sorts. Yeah. Let's look at these three sorts. Selection sort. Do we use order information in the selection sort? No. No. Because for selection sort, no matter what the order is, you get the same result, right? Yeah. There is only one case. Yeah. The best case, worst case, all the cases are the same case. Only one case. So it never uses the order information. Similarly, the bubble sort, it does not use any order information. Yeah. Okay? Yeah. But bubble sort is slightly different from the selection sort. The bubble sort in our textbook, there is an improved version. Okay? There is an improved version. Yeah, because if you look at the improved version, now, the idea is very simple. Every time when you do one round of processing, you use a counter variable to count the number of swaps. If at the end, if your counter example gives you the zero value, that means there is no swap. If there is no swap, then the whole array already sorted. So you should stop immediately. Okay? You should stop immediately. You do not need to, complete the remaining rounds. Yeah. So that's the improved version of the bubble sort. If you use improved version, then the order information, you use the order of the information. Yeah. All right? Yeah. Then insertion sort, that's quite different. Insertion sort, actually, we use the order information a lot. Why I say that? Why I say we use the order information a lot? Remember? Because with ordered information and without ordered information, the difference is huge, right? Without ordered information, it is big theta of n. With, if the data is ordered, here I should say this. If the data is ordered, yeah, so That's what we have here, because if the data is ordered, if the data is ordered, we have big theta of m. Yeah. So this special property of the insertion sort tells us insertion sort is a perfect example or perfect experience to be used in our current problem. Yeah. Closely related. Yeah. So we want to, make connection to the insertion sort, yeah, to help us get a solution of this current problem. Yeah. All right. Yeah. So that's the property for the insertion sort. Yeah. All right. Look at the details. Yeah. Yeah. Look at the annoying. There is some fly. Yeah. All right. Insertion step. We'll want to take another view on this insertion step, then connect to our merge step. Yeah. What's the relationship? Yeah. All right. This is insertion step, right? Yeah. The array already ordered, then we insert that V into this ordered array. That's insertion step. What's the connection? Yeah. This insertion operation and our merge operation, yeah. So we want to do the merge of two ordered arrays. What's the relationship? Yeah. All right. So we can see, actually, we can view in this way the insertion case. It's a special case of the merge case, because this subarray, we can treat it as one element ordered array. How about that? It is an ordered array, but it's a special ordered array. That's the insertion case. Special ordered array. So the merge case, we make it more general. Okay? So this subarray, we make a general ordered array. Okay? Generalize that insertion step. Okay? Yeah. So that's the relationship. Yeah. All right. So then, our work, our comparison work, we can also generalize from the insertion operation, the comparison work in the insertion operation. Yeah. Okay. All right. Yeah. Now you can see solution is, pretty straightforward. Yeah. All right. Yeah. All right. So let's look at the details of this merge step. Yeah. All right. For the insertion, the size, one is k and another is 1. Yeah. So it's not a balanced case. Yeah. All right. Yeah. So we want to, for the merge sort, first we want to fix this unbalanced data distribution. Yeah. That's the unbalanced data distribution. That's not good. That's not good. Yeah. So we want to improve it. Yeah. Because we have freedom to choose the data distribution, right? Yeah, we have the freedom to choose data distribution. Okay? Yeah. So when we have that freedom, we want to make balanced distribution so we can avoid poor worst case. Yeah. Poor worst case. Yeah. The insertion sort, or worst case, is very poor. How poor it is, insertion sort? Big theta of n squared. That is the meaning of the poor worst case. Yeah. in our new sort, we want to avoid this poor worst case. That is another technical problem we want to solve. Yeah. All right. Yeah. So now, with that into the consideration, when we split the data, we want to do even split, as even as possible. This fly is very annoying. Yeah. So, yeah. So apply here we apply the balancing principle. Yeah. So we try to make two subarrays of equal size. Yeah. So we split in the middle. We split the given array in the middle. Yeah. So you have even number of elements or odd number of elements. Even number of elements, so your two subarrays have the same size. But the odd, so one is one more element than the other. Yeah. So not too bad, very close. Yeah. Yeah. All right. Ooh, that fly is so annoying. Yeah. All right. C.2, merge operation. Yeah. So now we want to work out the details. Yeah. Yeah. Achieving balanced subarray, that's easy. That part is easy. Yeah. So we can do that part quickly. Yeah. All right. I use this line segment to show the splitting and merging ideas. Yeah. Make even split, yeah, as even as possible. Yeah. Yeah. First, we split in the middle. Yeah. If odd number, so then one is longer, just one more element than the other. Yeah. Then second round split. So first round split, second round. Yeah. So this is the first round. First round. Second round, left hand side, right hand side, yeah. And third round, okay, yeah, and so on. Yeah. Keep doing, yeah. Stop splitting when each file contains, each subarray contains one element. Yeah. That's the end. One element you cannot split. Two elements you can split another time, right? Two elements. Yeah, but one you have to stop. Yeah. All right. So then after that, so you have a sequence of small subarrays. Yeah. Then you do the merge. After that, then you do the merge. Every time you merge two adjacent subarrays. Two adjacent subarrays. Okay, all right. Then next round, yeah, two adjacent subarrays. Always two adjacent subarrays. Okay, yeah. All right, and then another round. Keep doing. The last round, you merge. Yeah. Suppose we have this operation. Okay, we just apply that operation to merge two ordered subarrays. So after the last round, we get the whole array sorted. That's the idea. Yeah. That's the merge sort idea. Yeah. Here you can see this is the critical step. After we solve this critical step, then we have the whole algorithm, merge sort algorithm. Yeah. All right. Yeah. Yeah. Yeah, because we do even splits all the time. Yeah. Even splits all the time. So our expectation, yeah, so we want to have worst case efficiency under control. Okay? Not very bad. Worst case efficiency, yeah. So actually the targeting worst case efficiency, big theta of n log m. N log m. Worst case efficiency. Much better than that n squared. Big theta of n squared. Yeah. Okay. Yeah. All right. Yeah. Next, we need to work out this merge step. Yeah. All right. For the merge step, let me use this diagram to explain merge step. There, this time, yeah. So, although we connect to insertion step before, yeah, but here, we need to, because it's different from the insertion step. It is different. Insertion step, remember we do shifts, right? Yeah. So here, we also need to consider the difference with that insertion step. Because insertion step, we need to do a lot of shifts. And here, you can imagine if we do shifts, it could be very complicated, right? Yeah. Because when you do shifts, here you have two ordered arrays. You need to consider shifts in the left ordered array and shifts in the right ordered array. Then the managing operations could be very complicated. Yeah. So for that reason, so we want to avoid that complexity regarding the shifts. So we don't want to do shifts. Too complicated. Yeah. So then we take an easier approach about the shifts. Easier approach. Okay, all right. So this time, we do this. Yeah. So we imagine some destination array. Okay? Yeah. So these two arrays, that's our input array. Two input array. Okay? Then this is our output array. Destination array, right? So output destination array, because we imagine the whole array at the end should be sorted. Yeah. Then we just want to arrange the elements in the input to the output array in certain way. Okay? Yeah, certain way. Yeah. Here we use the idea, that in-place idea, right? Yeah. It's in-place idea. Yeah. Every time we want to put one element in place. In-place idea. So if we use that in-place idea, then it's pretty easy. Yeah. All right, so let's do the work. Yeah. The first time we compare the first element in the left, right, two subarrays, yeah, A0, B0, okay, yeah. Then the smaller one, yeah, there is a smaller and a larger one. The smaller one, we know that is the minimum of the whole array, right? The smallest one is the minimum of the whole array. So we can put a smaller one in place immediately, yeah, because that's the first element in the destination array, right? Yeah, yeah. So here, yeah, this destination array. Okay, all right. Yeah. Then after the first comparison, we can put the smaller of A0, B0 in place. That's in the first position in the destination array. Okay, all right. Then, yeah, so for this case, here we just use one of the cases to explain the idea. Yeah. Then, in this example, so B0 is the max 0. Then the next comparison should be B0 and A1. Do this comparison. Then the smaller one is the second smallest element in the whole array. Then min 1 can be put in place after the second comparison. Okay? All right. So we keep doing that. Yeah? So the larger one, we need to do comparison with the next element in the other ordered array. Then the smaller one, we put it in place. Yeah. So we keep doing that. Keep doing that. Then the last one we put, this is last one we, after the last comparison, this is after the last comparison, we put second to last element in place, because the final one we do not need any comparison, right? The final one we do not need any comparison. Only one position left and one element left. So we just drop the last element into the last position to complete the sorting. Yeah? Yeah. All right. Yeah. So here you can see, yeah, because here you have the best case, you have the worst case. Yeah. The best case and the worst case. Let us consider the worst case first. This time we consider the worst case. Worst case means we need to consider the case that we need to do maximum number of comparisons. Not the minimum, maximum number of comparisons. So what's the maximum number of comparisons? You need to do comparisons from the beginning to and all the way to the second to last. Yeah, because the final one, the last one, we do not need. The last one, we don't. So the maximum number of comparison after the second to last element. That's the last comparison. Yeah. Then we can count. You need to count how many comparisons. You need to count. Okay. All right. To count that number, yeah, just number of elements. Yeah. You have k elements in the first array. You have k elements in the second array. The total number of elements 2k, but you do one fewer than the total number of elements, right? Yeah, one fewer, because the last one you don't do comparisons. Yeah. So the answer is 2k minus 1. Worst case, 2k minus 1. Yeah. All right. Yeah. But this is this merge case. We consider two subarrays with equal size. Size k, equal size. Yeah. Next, we want to generalize a little bit. Yeah. So we consider the general merge step. This time, we do not require these two arrays have the same size. Yeah. Not necessary. Yeah. Too restricted, right? Yeah. So we want to have a little more flexibility here. Yeah? Because in your real world applications, many times you need to merge two ordered arrays with different sizes. Yeah. So we want that formula. Yeah. So in that case, the worst case. Still, the same analysis. Yeah. And worst case, you can see the worst case, we need to do the last comparison to put the second last element in place. Yeah. And for the last element, no comparison. Yeah. Same idea. Yeah. So we can write the formula easily. Yeah. The total number of elements minus 1. Total number of elements minus 1. Yeah. So m plus n minus 1. That's the general formula. Okay? Yeah. Yeah. All right. Yeah. Yeah. So that's the general merge step. Yeah. Then we need to work on the best case. The general case. Yeah. We only need to work on the general case. Yeah. But this time for the best case. Then, to figure out the best case, now you need to consider the minimum, yeah? Because the best case corresponds to the case that you need to do the minimum number of comparisons. So what's that case? Now, under what special situation? You need to imagine that special situation. Under what special situation you can save maximum number of comparisons? You can save several comparisons, but you want to maximize your saving. Maximize your saving. Yeah, that's for the best case. Yeah. All right. So here the strategy. Yeah, the strategy. Try to exhaust one of the two arrays as early as possible. Yeah. What do you mean? Yeah, because exhaust. Think about when you have a situation, your first element in one of the two subarrays beats all other elements, all the elements in the other subarray. Beats. Yeah. Exhaust. You used up. Okay. You beats all of them. Okay. Beats all of them. You put all of them in place as early as possible. Yeah. The first one already. The first element in the subarray already, take care of all the elements in the other subarray. Then the remaining, you can put them in place directly, right? Yeah, because the remaining elements, they are larger than the first element in this subarray. Then you do not need comparisons. You can just drop them in place directly without any comparison. No. In that situation, the number of comparisons you need the same number of elements in the first subarray. That's the number. Yeah, because this one you need to compare with each of them. Okay? Yeah. So in this case, you need to m comparisons. M comparisons. But m comparisons, you do not know which number is larger, which number is smaller, right? M larger or n larger. You do not know. Yeah. Yeah. So you choose, your best case, you choose m number. You do m comparisons. That's the best case. The smaller of the two. M, yeah, if m, suppose m is smaller than n, yeah, so you choose m. If m is larger than n, you choose n. Okay? So the minimum of these two numbers, minimum of m and n. Yeah. So the exhaust the shorter array. Okay? Yeah. So the best case efficiency, the minimum of m and n. Okay? Yeah. Yeah. So that's the best case. Two formulas. So you have, for the merge operation, you have these two formulas. Yeah. The best case, you need to do this many comparisons. The worst case, m plus m minus 1 number of comparisons. Yeah. All right. So then you understand. Yeah. So you understand the merge step. Then, by the divide and conquer, the diagram we discussed before, we can complete the whole merge sort, right? Yeah. So now C.3, we want to do efficiency analysis for the merge sort. Yeah. When we do efficiency, we want to remember, we want to control poor worst case efficiency. Yeah. So we want to look at what is the worst case efficiency. Yeah. All right. Yeah. We use a recurrence relation to tell us how many comparisons do we need for the merge sort. Yeah. So let us estimate worst case efficiency. Yeah. All right. We use this T function represent the total number of comparisons for the, using the merge sort for the worst case. Yeah. T of n, capital T of n. All right. Then even split. Yeah. So we split into two subarrays. Yeah. Then divide and conquer. When you conquer each subarray, the number of comparisons you need for each subarray, T of n over 2. So although you take floor function, ceiling function, because here we do estimate, right? So here we do estimate. So that floor function, ceiling function, we do not bother to use them. Yeah. All right. Yeah. So T of n over 2. Yeah. Estimate. Yeah. Right. Then merge two ordered subarrays. The worst case, the exact number should be n minus 1, right? Yeah. But here we drop that minus 1, yeah, because we do estimate. So that small number minus 1, we want to make it simpler, so we just use n here. Yeah. All right. Then we can write recurrence relation. Yeah. For one element array, no comparison. For two element array, one comparison. Then the general case, yeah, T of n equals 2 times. Yeah. So here you need to pay the cost, the conquer step. Conquer the first subarray, T of n over 2. Conquer the second subarray, another T of n over 2. So 2 times T of n over 2. But then combine step. You need to combine. Okay? The combine step, you merge two ordered array, so you need n comparisons. Yeah. Approximately, yeah, n comparison. So you get this recurrence relation. Okay? Yeah. Next, we need to solve it. Yeah. To solve it, yeah. So we want to consider a simpler case. Yeah. So here the strategy. When we solve a problem, yeah, here, this is our current problem. We need to find the expression of capital T of n. To solve it, the strategy, we want to consider the simplest case, right? Yeah. At the beginning, we always will want to work on the simplest case. Here, what's the simplest case? Because here, you need to think about n over 2. You have a lot of n over 2. And you do recursion. Yeah. So n over 2, n over 4, n over power of 2, all the way down to the bottom. That's the recursion process. Yeah. So you need to consider how to handle all those power of 2 at the denominator in your capital T function. Power of 2 at the denominator. Yeah. So the simplest situation, that is where n is power of 2. When n is power of 2, then you can easily take care of all those power of 2 denominators, right? Yeah. So you can do cancellation easily. Yeah. All right. So then, for this special case, then we can rewrite our recurrence relation, yeah, in a new way. Yeah. Yeah. All right. Then we need to solve this new form of recurrence relation. Yeah. So here we do special transformation. Yeah. We do division. Division by 2 to the k both sides. After you do this transformation, you can see, yeah, so, yeah, why we do this transformation. Yeah. The goal is, when we do transformation, the goal is we want to make the left-hand side the main term of the left-hand side and the right-hand side. So these two terms, they have the similar form, right? Yeah, see? The structure, they have the similar structure. That property is important. Similar structure property. That is important. Yeah. So we want to, how to take advantage of this similar structure property. Yeah. We introduce a new function. Yeah. Yeah. New function. So here, let's define a new function. G of k equals this fraction form. Yeah. New function. Then, if we introduce this new function, then our recurrence relation becomes much simpler. Right? Yeah. Substitution. Yeah. So new equation, g of k equals g of k minus 1 plus 1. Yeah. So much simpler. You don't have those fractions, denominators. Yeah. So we want to find the g function first. If you can find g function, then t function comes out immediately. Yeah. All right. Yeah. Initial value of g, so you're plugging when k equals 1, so you have initial value of g function. Yeah. All right. Then we do recursion. Yeah. Yeah. So, because the g of k minus 1 equals g of k minus 2 plus 1. 1 plus 1, you have this 2. Yeah. Yeah. The second time you apply this recursion, yeah, so you get that number. Then we keep doing this, and the last equation, last equality, when we want to write, we want to use the initial value, g of 1, initial value. Yeah. If g of 1 is here, what number should be here? That simple question. How to answer that simple question? Yeah. We encountered this situation a few times before. Yeah. Yeah. So here I want to remind you, so any of you, you can connect to our old experience, similar situation we had before, how to keep track of the data. Remember that topic? Keep track of the data. Yeah, because here, when we have this ... thing, we get lost. We feel it is hard to keep track of the data. We need to find some special way to help us keep track of the data, right? Yeah. Yeah. Remember the idea I mentioned in our first lecture. I already mentioned that. Invariance idea. Invariance idea. Invariance idea. Okay? Yeah. So what's that invariance? Yeah. We need to, yeah. Yeah. What is k minus 1 plus 1? We add up these two numbers. K minus 1 plus 1. Yeah. Equals k, right? The sum of these two numbers. What is k minus 2 plus 2? Sum of the, also k, right? Yeah. So the sum of these two numbers, that is the invariance. Yeah. Same number k all the time. Okay? Yeah. All right. Then, now, the bottom one, you know, because this side, it should be k of 1, right? And what number here? K of 1. Because sum must be k, so it should be k minus 1, right? right? Yeah, yeah. All right. Based on this, yeah. So that invariance k, yeah, based on that, it should be g of 1 plus k minus 1. Okay? Yeah. So here, we review that invariance method to keep track of the data. Okay? All right. Yeah. Then, yeah, you plug in the initial value, so you get this k minus 1/2. Yeah. That's your g function. Yeah. G function, then you go back to the, you go back to the, original definition here. Yeah. Yeah. Then you can get a t of 2 to the k equals this expression. Yeah. All right. But you need to go back to the n in terms of n. Yeah. Because k is a temporary variable. Yeah. So we need to go back to the original variable n. Yeah. N equals 2 to the k, so k equals log base 2 of n. Yeah. So then we can estimate, because we do estimate. Yeah. Yeah. Not necessary exact formula. We don't need that. We just want a closed formula. So t of n approximately equal to n times log base 2 of n. Yeah. So here we drop that 1 minus 1/2. So yeah. Now you can see this is the worst case efficiency. This is the worst case efficiency. And it is much better than big theta of n squared, right? Yeah. So we get what we need, that is avoid poor worst case efficiency. Here we avoid it. Yeah. So this one is acceptable. It's not poor. It is acceptable. Okay? Yeah. Actually, if your worst case is this well, that's the best you can get. That is the best you can get for the worst case. You cannot do better than this. Okay? Yeah. Yeah. All right. Yeah. But some students may argue, because here we only consider the special case, n is power of 2. Yeah. If n is not power of 2, how do you see it? Right? Yeah, because n may not be the power of 2, right? You need to consider the general n. Yeah. So for the general case, yeah, definitely we need to do general n differently. Yeah. Not as easy as we did here. Yeah. But for the general case, we get the same result. Yeah. But for the details, I leave to part D. Part D, when we do the quick sort, we have the similar recurrence relation, and in that case, I need to use another method to do the estimation. The method, yeah, I introduce another method to do the estimation, yeah, but I leave it to the quick sort, part D. Yeah. Okay. All right. Yeah. All right. Yeah. So now, so we have 10 minutes before the end of this class. Let me do one example. How about that? One special selection problem. Find median of 5. Actually, this question is very challenging. Okay? Yeah. Pretty challenging for most people. It's pretty challenging. Yeah. All right. But for us, yeah, Yeah, because we have learned a lot of knowledge in computer algorithms. Yeah. So for us, it may not be that hard. Yeah. Actually, this question, find median of 5, I split this question into a few other questions, or you already did in your homework assignment number 1. Homework assignment number 1. There are 2 questions related to this one, and you already did it. We just put them together, you can get a solution of this question. Okay? All right. Yeah, so let's do it. Yeah. So we only need a few minutes, so we can complete it. All right. Before we complete it, let me say a few words about the relationship of this question with another related question. Yeah. Let me make that connection. Yeah. Before we work on the solution. So, what's the other? The question we just did in our last lecture. Yeah. Monday's lecture. Monday's lecture. Do you remember we have a question? Sort 5-element array. We did this example in our Monday's lecture. This question related, right? Median of 5. Same number of elements, 5 elements. Yeah. They are closely related. Yeah. All right. So for that question, our answer, here the answer, 7 comparisons, right? We can use 7 comparisons to sort that 5-element array. Yeah. Yeah. That means when you solve this problem, you should not use more than 7 comparisons, right? Yeah. Because the worst we can do, we can sort the 5-element array, then we pick the median. So the worst we need is 7 comparisons. Yeah. But actually, finding the median, we do not need to sort, right? Yeah, you do not need to sort. When you sort it, you do more than necessary. You do more than necessary. Yeah. So you can save a little bit. Yeah. If you only need to find the median, you can save a little bit. That means you should do better than 7 comparisons. So our target is 6 comparisons. We need to do at least 1 fewer comparisons, right? So this is our target. Okay? Yeah. So let us try to use 6 comparisons to find the median of 5. Yeah. Yeah. That's pretty challenging. Yeah. All right. So let me where is my remote control? Oh, here. I put in some. Yeah. All right. Yeah. So okay. I only have a few minutes. I need to solve it quickly. All right. Yeah. When we start tournament method, okay. We're familiar with the tournament method, right? Yeah. The first round, let's do tournament method. X1, X2, and we assume X1 is the winner, okay? X3, X4, second comparison number 1, comparison number 2, and we assume X3 is the winner. Right? Then another round comparison number 3, and we assume X1 is the winner. Okay? Yeah? All right. And in this round, we do not touch X5. Yeah. Okay? We do not touch it. Okay? All right. Then let's do some cleanup work. Yeah. Yeah. Summarize it. Yeah. Before we go to the next round. Yeah. All right. So what do we have so far? This diagram to represent X1 higher than X3 higher than X4 and X2 here. Yeah. All right. Then X5. All right. That's the current state. Yeah. All right. Next, elimination method. So this round, elimination. Elimination. Which element can be eliminated? Yeah. One of the question in our homework assignment 1. Okay? There is one multiple choice question. Because X1 is greater than 3 elements. X2, X3, X4. And the median, we know, median is the third largest, right? Third smallest, third largest, third smallest, right? The median, because here, median equals third smallest. Third smallest, but here you already, X1 is greater than at least 3 elements. Then it cannot be the median, right? Yeah. Or you can look at it in this way. Yeah. I need to complete it in 2 minutes. Okay? All right. So X1 can be eliminated. How about that? X1 is gone. Okay? Because it cannot be the median. Right? But after we eliminate X1, then the median becomes second largest, right? Second largest in the 4 element, the remaining X2, X3, X4, X5. All right? Yeah. Then the last round we do. So we have X2, we have X5, and we have X3, we have X4. Yeah. And our goal, we want to find the second largest in these 4 elements. That's the median. Yeah. Look at what do we need to do here. All right. All right. Comparison number 4. Number 4. And we can assume X2 larger than X5. So then, yeah. All right. Comparison number 5. Yeah. So, you know, yeah. The winner is the largest. Okay. Winner is the largest. Yeah. So if you assume X2 largest. Okay. All right. So that's comparison number 5. X2 largest, then the last comparison is number 6. Yeah. So the winner of X5 and X3, that's the second largest. Because X4 cannot be the second largest. X4 already less than X3. Yeah. So we do not consider X4. So the last comparison is the winner of X5 and X3. Yeah. Okay? That's the second largest. Yeah. Then we solve it. So we use 6 comparisons. We find the median of 5 elements. Yeah. Okay? Yeah. All right. Yeah. So we complete this question. So this is a very challenging question. Yeah. So if you give it to your, IT friend, if you have friends working in IT industry, yeah, so you can challenge them. Last time I asked, you can challenge it by the sorting 5 element array. So this time you can. This is another question, very challenging. Yeah. Yeah. All right. So let's stop right here. But we have another 2 special selection examples. So I will do next time. Okay? Yeah, those 2 examples also very important. So at the beginning of our Monday's class, I will do those 2 examples. Yeah. All right. On Friday, you will get your home assignment number 2. Okay? Yeah. So that's our last big assignment. Yeah, because then we have final. Yeah. If we do not include the final, then that's our last assignment. Yeah. All right. So that's it. See you Monday.